Patterns shape our universe, from spiraling galaxies to the symmetry of snowflakes. In materials, this order appears as crystals. Think salt or diamond, where atoms form a repeating lattice. This spatial repetition gives crystals their unique properties and underpins modern technology like the silicon chips in our devices. For decades, we believed crystals could only be ordered in space, not time. Physics taught us that at the lowest energy, matter should be perfectly still. No motion, no change. The idea of a crystal that moves on its own seemed impossible, like a perpetual motion machine. But science thrives on challenging assumptions. What if order could repeat in time, not just space? Imagine atoms locked in a rhythmic dance, ticking like a clock even at their lowest energy. This once theoretical question has led to a groundbreaking discovery, a new state of matter that could reshape our future. The time crystal has emerged from the quantum world, defying what we thought possible. Enter the time crystal, first proposed by Frank Wilczek in 2012. He wondered, if crystals break spatial symmetry, could something break time symmetry? Repeating motion without an external clock? Imagine a pond that, even at rest, ripples forever in a steady beat. That's the essence of a time crystal, a system that ticks perpetually, even in its lowest energy state. At first, scientists doubted it could exist without violating thermodynamics. But time crystals don't create energy. They're more like frictionless pendulums in quantum systems. Experiments soon confirmed their existence in isolated quantum systems, like chains of atoms or defects in diamonds. These early time crystals were hard to create and observe, hinting at a vast, unexplored frontier. The challenge: make this phenomenon accessible and useful. The leap from theory to reality was swift. Early time crystals were hidden in complex labs, far from practical use. The breakthrough? Creating time crystals from light itself. By trapping light in microcavities, scientists made photons and atoms oscillate together in a stable rhythmic pulse. These light-based time crystals tick at optical frequencies, making them easier to study and integrate with technology. This connects time crystals to the world of optics, opening new doors for communication and computation. We're moving from curiosity to building block. Time crystals could revolutionize quantum computing, clocks, and sensors. The temporal dimension is now a resource we can engineer. To understand time crystals, think symmetry. Regular crystals break spatial symmetry. Atoms pick a repeating pattern in space. Time crystals break time translation symmetry. Even at rest, they choose a rhythm, repeating motion at regular intervals. It's like a featureless plate gaining a special direction when you place a P on its edge. Suddenly, there's a preferred spot. A time crystal does this with time, creating a persistent beat in the flow of time itself. This is a fundamentally new phase of matter, defined by order in time, not just space. It expands our definition of what matter can be. Time crystals force us to rethink the quantum world's possibilities. They're not just a new material, they're a new way to organize reality. The discovery opens a new chapter in physics. The strangest part of time crystals: their ground state never rests. Traditionally, the lowest energy state means total stillness. No motion, no change. But time crystals keep oscillating, even at absolute zero. Imagine a pendulum that never stops swinging, even with no energy input. This perpetual motion doesn't violate physics. It can't do work or generate energy. The motion is locked within the quantum system, a stable feature of its lowest energy. True time crystals exist in non-equilibrium, driven by a steady input, but responding with their own rhythm. They transform constant input into a ticking output. thanks to collective quantum interactions. Time crystals are eternally restless, a new dynamic state of matter. Imagine a clock that never needs winding or a battery. That's the magic of a time crystal. Its ticking is powered not by energy, but by the quantum rules of nature itself. Its rhythm emerges spontaneously, a perfect, unending dance, offering a new kind of stability for future technology. Scientists discovered that by harnessing the powerful interaction between light and matter, they could create time crystals in the lab. Imagine a mirrored room where light bounces endlessly, interacting with atoms inside. The photons and atoms become so intertwined, they act as one. The result? A visible rhythmic pulse of light, a time crystal made real and observable. To make this dance between light and matter happen, you need to build a very special stage. This stage is a device known as an optical cavity or resonator. At its simplest, it consists of two highly reflective mirrors placed facing each other. The quality of these mirrors is astonishing. They can be so perfect that a photon of light might bounce between them hundreds of thousands or even millions of times before it has a chance to escape. This extreme confinement is what allows the light to build up in intensity and interact very strongly with any atoms placed inside the cavity. The cavity acts like an echo chamber for light, amplifying its presence and its influence. The process often begins with a steady, continuous laser beam aimed at the cavity. This laser acts as the energy source, but it is important to remember that the laser itself is not pulsing. It provides a smooth, constant stream of photons, like a river flowing steadily. This constant input is what scientists refer to as the drive. It doesn't tell the system to oscillate at a particular frequency. Instead, it provides the energy that allows the system to organize itself. The goal is to see if the system, when fed this steady diet of light, will spontaneously decide to start ticking on its own, at its own distinct rhythm. Creating these systems requires incredible technological precision. The optical cavities are often microscopic, fabricated on a silicon chip similar to the ones in your computer. These are not large tabletop mirrors, but intricate structures etched with nanometer accuracy. The atoms used are sometimes cooled to just a fraction of a degree above absolute zero to slow them down and make them more controllable. Advanced laser systems are needed to provide the exceptionally stable and pure light required to drive the system without introducing any unwanted noise or jitter. It is a symphony of high-tech engineering, all designed to create the perfect conditions for this new state of matter to emerge from the quantum foam. Within this precisely engineered environment, something amazing happens. The atoms and photons become so strongly coupled that they can no longer be described as separate entities. They form hybrid particles known as polaritons. These polaritons are part light, part matter, and they are the true actors in this temporal play. It is the collective behavior of these hybrid particles, influenced by the constant stream of laser light, that can lead to the spontaneous emergence of a periodic oscillation. The optical trap doesn't just hold the light and atoms, it transforms them into a new collective being, ready to break the symmetry of time. The creation of a time crystal isn't about a single atom, but the crowd, millions of particles acting in unison. In the optical cavity, photons act as messengers, coordinating atoms like a conductor leads an orchestra. Nonlinearity creates feedback, amplifying tiny changes into a stable, repeating rhythm. The system transforms steady laser light into a ticking clock, a time crystal born from collective quantum behavior. In the optical cavity, a steady laser fuels a fascinating process. At first, the light seems chaotic, like simmering water, but soon a new order emerges. the system locks into a natural rhythm, flashing on and off with perfect regularity. This is the heartbeat of the time crystal, an emergent, stable rhythm from light and matter. The secret to a time crystal's rhythm isn't in a single atom, but in the power of the collective. When thousands of atoms interact through shared light, they synchronize, like a flock of birds or a crowd moving as one. The whole becomes more than the sum of its parts, a stunning unified dance. Visible time crystals allow us to directly observe their temporal pattern. The evidence is in the light escaping the optical cavity. A photodetector counts photons, revealing a periodic wave of light pulses. This blinking light confirms the time crystal's existence. Scientists can now study and understand this phenomenon in real time. This accelerates discovery, turning abstract concepts into measurable reality. Time crystals could revolutionize quantum computing. Their stable rhythmic motion offers a new way to encode, honey, and protect quantum information, making qubits more resilient to errors. Acting as an ultra-precise quantum metronome, a time crystal could synchronize millions of qubits, unlocking new possibilities for computation and transforming the future of quantum technology. Time crystals created with light open a new frontier in optics and sensing. Their stable oscillations could revolutionize lasers, metrology, and sensing, enabling ultra-precise clocks, advanced navigation, and next-generation photonic circuits. This breakthrough may transform how we measure, communicate, and interact with the world at the most fundamental level. Beyond the immediate applications in computing and optics, understanding how matter can self-organize in time opens up a new frontier in materials science. For centuries, we have designed materials based on their static properties, their strength, conductivity, or hardness. Time crystals introduce the concept of active or living materials, substances with intrinsic self-sustaining dynamics. Imagine a material that can automatically regulate its own temperature by oscillating between a reflective and an absorptive state, or a surface that can perpetually clean itself through a rhythmic microscopic motion. Time crystals provide the first physical example of such emergent temporal functionality. This research pushes us deep into the realm of non-equilibrium physics, which studies systems that are not in a state of thermal rest. Most of the universe, from living cells to stars, exists far from equilibrium. By studying how time crystals maintain their ordered motion, we can learn fundamental principles for designing other complex, functional materials that operate in a dynamic state. This could lead to breakthroughs in areas like soft robotics, where materials need to bend and move on their own, or in biomedical engineering, where we might design smart drug delivery systems that release their payload in periodic controlled bursts. The ability to control a material's properties with a steady non-periodic input, like a continuous laser beam, is also honestly revolutionary. This points toward a future of light-controlled, programmable matter. We could develop materials whose mechanical stiffness, thermal conductivity, or electrical resistance can be switched on and off in a periodic fashion simply by shining a steady light on them. This would allow us to create adaptive structures that can change their function on demand, such as an airplane wing that can dynamically alter its shape to optimize airflow, or electronic components whose behavior can be reconfigured in real time using light signals instead of complex wiring. Ultimately, the discovery of time crystals forces us to rethink the very nature of matter. It shows us that order can exist not just in the static arrangement of atoms, but also in their persistent collective motion. This conceptual shift is likely to inspire new ideas across countless scientific disciplines. Just as our understanding of spatial crystals gave us the semiconductor revolution, our newfound ability to create and control temporal crystals may lay the groundwork for a future filled with dynamic, responsive, and intelligent materials that we are only just beginning to imagine. The future of materials may not be static, but rhythmic. Time crystals are a marvel of quantum physics, but their delicate order is easily disrupted by even the slightest environmental noise. Most require extreme cold to survive, making real-world use difficult. The quest is on to create stable, room-temperature time crystals, unlocking their true potential beyond the lab. Beyond stability, scaling these systems for real-world use presents significant engineering challenges. Current experiments are small, involving limited atoms in a microscopic optical cavity. These setups are far from the large interconnected systems needed for practical applications. Can we manufacture and link millions of these units reliably? This requires new techniques and technologies. The complexity of these systems is another barrier. Creating a time crystal is not as simple as mixing ingredients. It requires precise engineering of light-matter interactions. Parameters must be tuned perfectly. A slight error can prevent formation. This makes design and reproduction difficult. We need a complete theoretical understanding to predict and control behavior with certainty. The definition and utility of time crystals are still debated. The community is working to understand their formation and behavior. Are all observed time crystals new phases of matter or complex classical oscillations? How do we distinguish between them? A deeper theoretical foundation is necessary. We are still mapping this new temporal continent. Integrating these components with existing platforms is challenging. Creating a time crystal in isolation is one thing. Making it talk to a silicon waveguide or qubit is another. This requires solving materials compatibility, energy efficiency, and signal conversion challenges. Time crystals cannot remain standalone curiosities. They must be integrated into the broader technological ecosystem. The path from discovery to technology is long, and for time crystals, the journey has just begun. We stand at the edge of a profound shift in our understanding of the universe. The discovery of time crystals marks a new frontier, where time itself becomes an engineerable dimension. These rhythmic entities bridge the quantum world and technology, offering stability and precision. The time crystal story is a testament to human curiosity and the wonders yet to be discovered. The future is being shaped by the rhythm of time itself. Time crystals promise technology with quantum precision, transforming our daily lives and unlocking new possibilities. We are moving from observers to architects of time, forging a path into a world we are only beginning to imagine. Thank you for joining us.